Spearman's rank correlation coefficient is a different way of testing the correlation of two data sets. And the most typical method is just using the Pearson's correlation coefficient, Pearson's moment correlation coefficient, but the alternative is also Spearman's rank correlation coefficient, which has its own benefits. Some of the advantages it has over the Pearson's moment correlation coefficient is that it can be used for data that's nonlinear, and you should know that Pearson's moment correlation coefficient is only used for linear data. So it can also be used for data that has been ranked. So for example, if you're given a data set and they already told you, oh, we've asked people to rank these things, then it would be hard to use Pearson's moment correlation coefficient, but it is possible to use Spearman's rank correlation coefficient. Because what Spearman's test does is that it uses the ranking of the data values. So if something's already been ranked, you can easily use this correlation. But if it's ranked and you don't have the original data, you can't use Pearson's moment correlation coefficient. And it's not affected by outliers, whereas the Pearson one is affected by outliers. So there are many advantages to this method. The calculation steps are similar to correlation coefficient, but the beginning will be slightly different, and that's the only addition to this test. So if you know how to do correlation coefficient, this only has a few additional things. So I'm going to have a running example here, while on the left I'm going to have the explanation. So you want to look at your x and your y data separately. So the process we're going to do, you're going to do to your x, and then you're going to do to your y. And what you're going to do is you're going to rank the data. So you're going to give each data set a ranking, and you're going to start by giving 1 to the highest value, and you're going to continue in increasing order. So if I have this table, and I'm going to rank my data. So from the x, the highest value is 45, so this is going to have 1. And then my next highest value is 34, and then we have 29. So I'm ranking them here. Now notice that 23, we have two 23s. In the case that you have two values, you're going to take their average. So the two 23s are meant to have a ranking of 4 and 5. So what I'm going to do is take the average of 4 and 5, which is 4.5. So this is going to be 4.5, and this is going to be 4.5, which means the last one is going to be 6. Okay, so they both take the position of 4 and 5. And we're going to repeat the same thing for y, but again starting from 1 from the highest. So 1, 2, and then I have 11 will take, both 11s will take the position of 3 and 4, so I'm going to have 3.5 as their average. And then 5, because 3, they'll take up 3 and 4, which means the next one is 5, and then 6. So I have this data here. And next what I'm going to do is take this new table and I'm going to put it in my calculator. So you're going to use the same process. I'm going to go to edit, I'm going to add my values in there, and then I'm going to go to stat, and I'm going to select calculate, and then the fourth option, which is linreg, so linear regression. And what's going to appear is this screen, so make sure that you have the correct L1 and L2 in your list, and also make sure that your frequency list is empty. You're going to press on calculate and you're going to get this page. And just as with correlation coefficients, you're going to take the R value, so that's going to be your Pearson, your Spearman's. You're going to take the R value, and that's going to be your Pearson's rank correlation coefficient. So we have, and we donated with our subscript S, that's the IB notation, so S for Spearman's, and our value is negative 0.956 to 3 significant figures. Now, what does that actually mean? Well, interpreting the values will be similar to the Pearson's moment correlation coefficient. So we have values, your R value will be from -1 to +1. But what it tells you is to what extent one variable increases or decreases as the variable increases, as the other variable increases. So what you're going to always talk about is your x increases, and so what happens to your y. If it's positive, then it's increasing. If it's negative, it's decreasing compared to x increasing. If it's completely 1, then your data is strictly increasing. And if it's negative 1, then your data is strictly decreasing. These type of data sets are called monotonic. And obviously, the closer to 0, it means that there's a weak association between them. So there's not a consistency in being increasing or decreasing. What about our data that we just calculated? So this was the value we calculated. And let's say my x was the time spent training, so how much I spent training, and y is how long it takes me to run 2 kilometers. And the way I want you to interpret it is first translate it. So our value is telling us that it's a positive, our value is telling us that it's a negative, it's a strong negative correlation. Okay, so what it tells us is that as x increases, y decreases. Now, what I want you to do is instead of x and the y, replace it with the wording here. So we can say that it's a strong negative correlation. So that means the more hours you train, so this is us translating as x increases, the more hours you train, the faster you can run the 2 kilometers. Or alternatively, you can say the more you train, the less time you take to run 2 kilometers. But I don't want you to blindly write these sentences, just translate decreasing as less than. Less time taking to run 2 kilometers also means that you can run the 2 kilometers faster. So try to actually interpret what your data means. If it's a positive correlation, then it would take a longer time to run the 2 kilometers. So do interpret it. And if it was a 0 correlation, then you can say there's no correlation between the data, and similarly. So the interpretation would be similar to Pearson's moment correlation coefficient.